Hello and welcome. You are looking at the Polygon Angle Sum Theorems. Alright, let's start by talking about what a polygon is. It is an enclosed two-dimensional shape, such as these two right here, whose number of sides is equal to its number of angles slash vertices. So another word for angles is vertices, so I might use one or the other interchangeably. It's not intentional, I just end up saying one or the other. So anyway, there are, in this five-sided shape, there are five sides, and just the same there are five vertices, 1, 2, 3, 4, and 5. In this four-sided shape, there are four vertices, 1, 2, 3, and 4. So that's always going to happen. Every angle is met by the endpoints of two segments only. Let me even underline that. So for example, this would not be a polygon because these endpoints don't even meet at an angle, and this would also, and it's not enclosed, and this would also not be a polygon even though it meets everything except the last sentence. It has 1, 2, 3, 4, 5, 6 sides, 1, 2, 3, 4, 5, 6 angles. It is enclosed, it is two-dimensional, but the problem is that these angles here are not met by two endpoints only, they're met by multiple endpoints. So that does not satisfy the definition. Polygons have to kind of have an inside where it's not, where it's enclosed, but they don't intersect in some way. Polygons have a minimum of 3 sides, and that's a triangle. So that's the smallest kind of, not like in size, but that's the smallest sides-wise polygon you could make. And it does not have an upper bound for how many sides it can have. So it can have 20, it can have 100, it can have 1,000, etc. Now, circle's not a polygon. However, the more sides you get in what's called a regular polygon, I'll be sure to be explaining that in a few minutes. Like, I can go up to 16 here. I have a polygon tool. The more sides you get, as you can see, the more circular it becomes. So if I had a 1,000-sided polygon, you might actually mistake it for a circle because the sides are so difficult to see where the angles are meeting and everything else. So it can become circular in nature, but a circle doesn't have sides. It doesn't fit this definition. So a circle is not a polygon. Okay, the diagonals of a polygon are the segments that can be drawn between non-adjacent vertices. So vertices that are adjacent would be, say, this one and this one. Those are adjacent. But non-adjacent vertices would be this one and this one. They aren't neighboring each other. There is another vertex between them, another angle. So if I draw like a dotted, a dashed line here, this is called a diagonal. It's not necessarily always diagonal. In fact, this is also called a diagonal. The diagonals are going to angles that are opposite them in such a way that they are not adjacent to them. It's not near them. Those are two diagonals. These are two diagonals, etc. In fact, these are all of the diagonals in this five-sided shape. Oh no, let's see, is that it? Oh, and this one right here. There, see, I can make a star. So I can make 5 diagonals in this five-sided shape. It's kind of cool. And then this one here has some diagonals I'm going to talk about in 1 second. Polygons by nature will either be convex by default, like this kind, or concave, the more irregular looking ones, the ones that start to stick in, and that literally is concave. That's what that means. A convex polygon has all diagonals inside the polygon, whereas a concave polygon, although here's a diagonal that's inside the polygon, here's one that's outside of the polygon. It will have at least one outside of it. So as you can see, that is one way to fit the definition of convex polygon. Another way, concave polygon. Another way is to say that one of the interior angles has a convex angle, such as that one right there. Or I could talk about one of the exterior angles having a concave angle. So an angle less than 180 degrees versus an angle greater than 180 degrees. Polygons are named by their vertices in circumnavigating fashion. By that I mean, let's say I named this one here with these letters. I have to start at one of the letters. Let's say I started at A. It's called polygon A. After that, I must go to my next vertex above or below it. You know, I have to go adjacent to it. So let's say I went to C. If I went to C, then I have to go to B next, and then D, and then E. So it should close back out at A. I won't put A again, but it should close back out there. So this is an appropriate way of naming this polygon. Another appropriate way, if I started at D, I could go this way. I could go B, C, A, E. I am circumnavigating the polygon. And right here, I'd be doing the same thing. So you have to traverse the sides. What you cannot do is traverse the diagonal. So if I started at A again, I could not go across to D, then up to C, over to B, and down to E. That is not an appropriate name for this polygon. Another way of thinking about it is, let's say they didn't give you a diagram, and they wanted to tell you information about the polygon. They even wanted to tell you the name of the polygon. What an important tool is for that is to be able to know how to draw it. So you might not know how to draw it exactly, but at least when they say something about an angle measure, like once again, if I had I think I said ACB or something like that. If I wanted to talk about polygon ACBDE, and I wanted to talk about angle ACB, I better have drawn it in such a way that A connects to C and connects to B. If I said polygon ABCDE, and then I wrote it like this, and then talked about angle ACB, that wouldn't make any sense if I didn't draw it this way. So that's just kind of the idea behind it there. And like I said, this is the same way, it's just it's 4 sides instead of 5. Okay, so let's start talking about the sum of the interior angles of a polygon. So I'm going back to this equilateral 5-sided shape again. Pay no attention to the fact that it's equilateral, but that it's a 5-sided shape. We now know that the sum of the interior angles of a triangle is always 180 degrees. So if I draw a triangle, then those 3 interior angles automatically add up to 180. It's just a cool fact about triangles. But we can also discover what the sum of the interior angles is of any polygon. And we can do, and they're not all 180, but we can do that by drawing some diagonals, because what's going to happen is whenever I draw diagonals in this guy right here, I'm going to make triangles. So when I draw a diagonal from here to here, and when I draw a diagonal from here to here, I have now created triangles where every interior angle of the triangle is a portion of the interior angles of the 5-sided shape right here. The problem is if I start drawing more diagonals here, yeah, I've made more triangles, but the issue now is that I've made triangles, and I've also made a 5-sided shape inside here, but now I've made triangles where there are interior angles that don't have anything to do with the interior angles of my actual 5-sided shape. So I'm technically using the angle addition postulate. If you think about it, I could call this angle A, B, C, D, E, F, G, H, I, or something like that. And I plus D plus A equals this entire angle here. B is this angle, C plus E is this angle, F plus G is this angle, and H is this angle. So what happens there is when I add up all the degrees in this triangle, which is 180 degrees, with all of the degrees in this triangle, which is also 180 degrees, with all of the degrees in this triangle, which is also 180 degrees, I get the sum of my 5-sided shape, and 180 times 3 is 540 degrees. So that's the measure of a 5-sided shape. This can actually work with all of our shapes of all of our different sizes. So let's do a 4-sided shape. I'm just going to draw one right here. It's going to be a terrible looking 4-sided shape, but I'm going to use one diagonal to make 2 triangles. And again, the angles, the interior angles of the triangle added up equal the measure of the interior angles of this 4-sided shape. Now this 4-sided shape has 2 triangles, both at 180 degrees each in terms of their interior angles. You add them up and you get 360 degrees. So now I have 3 consecutive angle measures for 3 different sets of sides. And what I can do now is I can kind of now formulate a conjecture based on a pattern that I'm noticing here. And what I'm noticing is that every single time, well, you might say something like, oh, I'm going from 180 to 360, so I'm doubling my amount. And I'm going from 360 to 540, so I'm doubling my amount? Not really. So you have to come up with another pattern. It's not necessarily doubling, but now you can say this is more of a linear approach. Every time I add a side to my triangle, it looks like we're adding another 180 degrees. And here you add another 180 degrees. So from 5 to 6, you'd also add another 180 degrees. Essentially, a 6-sided shape is another triangle built on to your shape. So now this has 1, 2, 3, 4, 5, 6 sides. So a six-sided shape is just another 180 degrees added, which is 720 degrees. So like I said, that keeps happening. You want to make a seven-sided shape, you could build another triangle on top of it. This no longer looks like an equilateral polygon here, but now that has 7 sides. And that is another 180, which is 900. So as long as you're good at adding your 180, or maybe you followed a lot of ice skating or snowboarding and skateboarding, and you hear that they do these tricks, 8 is 1080, you'll know these numbers by multiples of 180. You'll practice them a little bit, and they'll become familiar to you. So these add up to 180 each time. So it would be nice if we came up with a formula that said, knowing our number of sides, how can we find the angle measure? Or knowing the angle measure, the interior angle sum, how can we figure out how many sides there are? Well, here's another way of coming up with it. Because the problem here is, if you think of this like a graph, it's not going to cross at the origin. So in order to do that, we have to find a way to make this number 1 and 2 and 3, etc. That way we can multiply these by 180 and get our amount. So the question is, how do these numbers 1, 2, 3, 4, 5, 6, 7, 8 tie in with our number of sides? Well, you can not only see that these are 2 less than the number of sides each time, which is very important, but you can also see, in case you forget that, you can also see that this is the number of triangles that there are in each of the shapes. So if you recall, a triangle is, well, it's one triangle big. A quadrilateral, a 4-sided shape, which we're going to name later, is 2 triangles big. A 5-sided shape here is 3 triangles big. If you ignore this one right here, look at these ones. A 6-sided shape is 4 triangles big. So you can see how they build on, and 5-sided, or 5 triangles for 7-sided. So that's how it keeps building. This is number of triangles, if you want to think of it like that. So you could use a formula using the number of triangles. We're going to use the number of sides because that's going to be introduced more often in problems. It'll ask you, what is the sum of the measure of the interior angles with this number of sides? So go ahead and take a look at that. We have 3 sides for 180 degrees. So if we do the degrees here, that's equal to 180 times not 3, but the number of sides. I'm going to call this n, and this will be d. It'll be the number of sides minus 2, and that'll give you the number of triangles. You multiply the number of triangles by 180, and you get the number of degrees there. So let's do a couple of examples with that based on what we know, and it might be good to have a calculator handy here. So a couple things. First of all, we have to so for these problems, we have to use the angle relationships in each of the diagrams below to solve for the given variable. So in the first one, part A, we have a polygon that's 1, 2, 3, 4, 5, 6, 7 sides big. So the idea is if I add up all of these angle measures, I'm going to get, let's see here, 180 times, there are 5 triangles in a 7-sided shape. That's 7 minus 2. 180 times 5 is, what is that, 900? A 7-sided shape, now you might have this table with you, but a 7-sided shape has 900 degrees of interior angle sum. So if I add 138 with 106, with m minus 9, with m, with 133, with 120, with m plus 13, I get 900 degrees. So the idea is to solve for m. We already have the measure here. We have to find out what these, at least what m is, if not the actual degrees as well. We could do that. So combining like terms, let me whip out my calculator for this and do 138 plus 106 minus 9. I'm combining like terms, all the constants, plus 120 plus 13. On the left side, I'm getting 501 for those values. There are 1, 2, 3 m's, so that's 3m plus 501 equals 900. Subtract 501, 3m equals 399, and divide by 3. I should know that on top of my head. M, I think, is 133. If I'm wrong, please correct me, but I believe that's correct. So m is 133, that's for A, and you could substitute 133 into these to figure out the rest. And you could double check by adding them all up and make sure they add up to 900. Okay, B, I have a 1, 2, 3, 4, 5, 6-sided shape, all of them of angle measure x, so it's an equilateral 6-sided shape. We'll give another name for it in a moment. If there are 6 x's, that's also equal to the angle, number of degrees is this 180 times 6 minus 2, 180 times 4, that's 720. So 720 degrees in a 6-sided shape. Like I said, you might be able to refer to your own table if you write this down or have some mental note. You might remember it over time. I can't say that I remember all of them over time, but if you can add by 180 quickly enough, I think you'll be good. Divide by 6, that's x equals 120. So every one of these is 120 degrees. Okay, for C, here we have a, well, you have a 1, 2, 3, 4, 5-sided shape along with a 3-sided, triangle. But if you add them all together as well, you come up with a 1, 2, 3, 4, 5-sided shape as well. This is also a bigger 5-sided shape. So I need to solve for k here, so it'll be important to try and figure out what some of these other angle measures are. Like for instance, I know this is 180, so that's not necessarily an angle here, but I might use the 180. Based on some of this stuff right here, I need to know what this angle is in particular. That's the one that's really missing from this bigger angle. And the idea though is that this is an isosceles triangle, which means these pairs of sides are equal, which means their angles opposite them are equal. So if this is y, then this is y as well. So I'm just going to look at the triangle first, this inside guy right here. And I know that when I add up all of these angles, I get 180 degrees. 6 plus y equals 180, or 64. 64 plus 2y equals 180. 2y equals 116, and so y equals 58. So now that I have 58, I'm going to use that and substitute it into here. Now I actually do have all of my angle measures in the larger 5-sided shape, except for angle k. So if I add up 64, let's start using a different color. If I add up 64 with 58 plus 90, that's that's this whole angle right here, with 96, k, and 88, then I'm getting the sum of the interior angles for a 5-sided shape for this bigger guy right here. Remember, this is the one we're looking at. And a 5-sided shape goes up to, see, I can't remember already. I think it's 540 degrees. So you create that equation, it goes up to 540. Let's go ahead with the calculator again. 64 plus 58 plus 90 plus 96 plus 88 is 396. So going over here, I have k equals, or k plus 396 equals 540. Subtract 396. I don't trust myself in my head right now. So I get k equals 144. There's the answer to C. And D, now you have a 1, 2, 3, 4, 5-sided shape again. So we know that this is going to add up to 540 whatever we do. Now we are missing some angles here. We're missing this one and this one. However, they do tell us these are parallel lines, so assume for a moment that you might have to make use of that. So I don't know what these angle measures are. In fact, I don't know if I'll ever be able to figure out what they are. But I do know that when there are parallel lines and a transversal that is cutting through those parallel lines, that I am now looking at, if you tilt your head a little bit, same side interior angles. And one thing I know that's true about same side interior angles is that they add up to 180 degrees. So I may not know what these angle measures are, but I know that this plus this is 180. So as I'm adding up these 5 angles, I can say this one plus this one, 180, plus 135, plus 2y, plus 3y equals 540. And that's your setup. 5-sided shape. 180 plus 135 is 315. That's plus 5y. So 5y equals, what is that, 225? Let's hope. And so y equals 45, I think. So 45, I guess I'll put degrees for y. And that's it. And that's all for those ones. Now let's talk about regular polygons. So a regular polygon is what I was calling before an equilateral polygon. So a regular polygon has all congruent sides and angles. They will all be convex polygons. They'll all look like these ones right here, and they get, like I said, more circular. Even a 16-sided one appears to be more circular. The number of sides for this one is 3. The name of it is a triangle. Whoa. The interior angle sum is 180 degrees. The interior angle measures are each the same amount, all congruent sides and angles. So if these are each unknown values x, then 3x equals 180, so x equals 60. So you can actually find out the angle measures of regular polygons just by knowing the number of sides. Just by knowing the name of the polygon, you can now know the number of sides, and then you can divide by the number of sides. That was 180 divided by 3, and get the individual angle measures. So notice each time we do this, we're going to do the sum of the interior angles divided by the number of sides, or number of angles, if you'd like to put it that way. Four-sided regular polygon right here. This name, well, the name of the polygon, I want to make sure that I name that first. It's a quadrilateral. Otherwise, I could have put square here, which is what a regular four-sided polygon is, and a regular three-sided polygon is called equilateral triangle or equiangular triangle, but I didn't put that as well. I'm just putting the name of the shape. An interior angle sum of any quadrilateral is 360 degrees. It's another triangle added. And its interior angle measure, 360 divided by 4, that's 90. And that one makes sense. I think you're used to seeing that those are 90-degree right angles for a square. Okay, this one, the five-sided shape, you might know a building named after this. It's called the Pentagon. Five-sided shape. So I've been calling it a five-sided shape. Now you know its name for sure. Interior angle sum is 540 degrees. 540 divided by 5, the numbers start to get a little weird over time based on what you're dividing by. This one's 108 degrees each for those. In a regular six-sided shape, otherwise known as a hexagon, in a regular hexagon where all the interior angle measures add up to 720 degrees, if you divide 720 by 6, you get 120 degrees per angle measure. This is seven-sided shape. I don't know how much use we'll give to the regular heptagon because it unfortunately gives you dividing by 7 when this isn't really a good value to divide by 7, 900. In fact, I'm going to have to use the calculator for it. I'm getting 128.5714286. So as you can see, not a great value, about 128.6 degrees. Like I said, not one you're going to be using very often there. 8, although you're not looking at it in the best way possible, if you tilt your head a little bit, you're looking at a stop sign. These are called octagons. Interior angle sum is 900 plus 180, so that's 1080. And 1080 divided by 8, I don't believe is a good number either. Oh, no, it's a fine number, 135. The nine-sided shape, the nonagon, when you add all those up, that's 1260 degrees divided by 9 for the regular nonagon. You're getting 140 degrees per individual angle. And the 10-sided shape called the decagon has 1440 degrees divided by 10, that's 144 degrees. And then another shape that it's not drawn out here, but a 12-sided shape, just so you know the name, it's a dodecagon. It might be one word, actually, but that name will be used every so often for things. Okay, so a regular polygon with 3 sides, like I said, that'll be known as an equilateral triangle more so than a regular triangle. You'll see that more in a textbook, in a problem set, whatever it is. And a regular polygon with 4 sides is called a square. Exterior angles. You've heard of exterior angles before at one point already. The exterior angles here are these 3 measures, and in an equilateral polygon of any sort, then you are, or in a regular, polygon of any sort, then you are looking at the same angle measure for each of them. So they are the supplements of all of your interior angles. So 120 plus 60 would give you 180. So all these are 120. These, in a regular quadrilateral or a square, are 90 degrees. And here, I believe that number is 72. Now, when you add them all up, let's take a look at what they are. 120 times 3 equals 360. 90 times 4 equals 360. And 72 times 5, I want you to take a guess of what you think it is. Say it. Yeah, it's 360. What is the sum of the measures of the exterior angles in all polygons? It is 360 degrees, always. Doesn't matter if they're regular or not. But this is a good example of seeing those exterior angles as regular. Okay, last set of examples and we're all done. How many sides does a regular polygon have with exterior angles measuring at 40 degrees? So in this example, you're looking at some sort of polygon. I have no idea what the polygon looks like. I'm just drawing it. But when you're looking at the exterior angles, all of these are 40 degrees each. So the idea with this one, you can do this a lot of different ways. You could figure out what the interior angle measure is, add them up, then divide by the number of triangles, find the number of sides, etc. But an easier way here is there are a certain number of them that are 40 degrees. And remember, 40 times the number of exterior angles is 360 degrees. Because when you add 40 a bunch of times, you're getting 360. So divide by 40, the number of exterior angles is 9, which also means the number of sides, n is what we use for number of sides, is 9. So this is a 9-sided shape. If you need to know the name of that, it's a nonagon. So a lot of backwards thinking in these. What's up? How you doing? Good. I'm good. Thanks. Okay, number 2. A polygon has an interior angle sum of 2,520 degrees. That's a big number. How many sides does it have? So if you recall, when you add up the number of angles, interior angle measures here, you're going to get what's equivalent to the number of triangles in your polygon. So to figure out the number of triangles in your polygon, you subtract 2 from the number of sides, etc. So we have this formula here, if you will. So I'd substitute 2,520 in for my interior angle sum, and I'm going to work backwards there to solve for my number of sides, n. So I divide by 180, and that's calculator worthy. I'm getting 14. So that's how many triangles there are in the polygon, if you will. And if I add 2, I'm going to get n equals 16. So it's a 16-sided shape. If you don't know the name of that polygon, you just call it 16gon. And I'm not kidding. I'm serious about that. You would that's what you'd call it. 16gon. Number 3, each interior angle of a regular pentagon has measure 2x plus 4 degrees. What is x? So each one of these in the pentagon is 2x plus 4. Not just this one, but all of them. So if I add up all 5 2x plus 4 degree angle measures, or in other words, multiply it by 5, I'm getting the full interior angle sum of a pentagon, which was 540. That's what we've been working on before. So I can distribute, actually I'll divide by 5. Let's do that. 2x plus 4 equals 540 divided by 5, which you might now know is 108. So you might be able to start with your equation to be just like this. You might be able to set that up immediately, because if you used our previous table that we mentioned, you saw that each interior angle measures 108. So if all of them are that, you can make that equation. 2x equals 104, so x equals 52. And that's solving for x there. So a lot of workarounds, not just based on the notes, but the examples can use a lot of different things, and you have to use your knowledge to apply it. Fiend!